Okay, so here's the Chapter 12 review. I made some things in bigger font so they might show up better on the video. So problem 1, if you read through it, it talks about a trip to the dog park. And at the dog park there are 4 Labradors, 3 Boxers, 6 German Shepherds, 5 Terriers, and 4 Mutts. And before I even got into the word problem, I realized that it might be important to know how many total dogs that were at the dog park, so I just added up the numbers of each type, and it came out to be 22 total dogs. And the questions for this problem basically want me to use this data to predict the breed of the next dog that arrives, asks me to use empirical probability, and each of these parts are just going to be a fraction, because all probability questions will start off with a fraction answer. In the denominator, it's going to be the total number of dogs that were observed. In the numerator, it's going to be the total number of dogs with the breed that I'm looking for. And in this case, for part A, the probability of the next dog being a Labrador, there were 4 Labradors that were seen at the park out of the 22 dogs that were seen at the park. So the empirical probability that the next dog is a Labrador is 4 in 22, and I can reduce this without my calculator. So as I go through the review, any fraction that's reducible, I'll reduce it, and if a fraction can't be reduced, then I'll give a decimal approximation, and I'll give 3 decimals worth of accuracy. For part B, the probability the next dog's a Boxer, I'll just do 3 and 22 because there were 3 Boxers of the 22 dogs. That's not a reducible fraction. If I tried to reduce it on my calculator, I did 3 divided by 22 and then math, enter, enter, my calculator will show me that 3 over 22 just isn't reducible. That was a friendly problem. As problem 2 is supposed to be friendly, problem 2 talks about a multiple choice test that has 4 answers, or each question has 4 possible answers, so I can think of the potential answers being A, B, C, or D. And I'm going to answer one question, and I'm certain one of the responses isn't correct, so I'm not sure which one, but I know that. Let's pretend like I know that C is not correct. So now I'm going to guess, and what's the probability that I guess the correct answer? There should only be one correct answer, so the numerator is going to be the one correct answer I could guess. The denominator is going to be the number of answers that I may guess from. Because I've eliminated one of the 4 question answers, there's only 3 answers left, so that the fraction is going to be 1 in 3 for the probability of guessing on this question, where in general it'd be 1 in 4 if you didn't have any knowledge as to which of the answers was correct. So hopefully as you're watching the video, you already have worked out my review and checked your answers, and then you're either watching the whole video just in case I say something that's going to help you, or you're just fast forwarding to the portion of the review where your answers didn't match my answers. Part 3, 1 card selected at random from a deck of cards, find the probability the card selected is, and then I have to know something about a deck of cards to answer all of these questions, and each one of these is a probability question. I'm picking 1 card from a deck of cards. These aren't conditional probabilities, so each of the parts of number 3, A, B, C, and D, are going to have 52 in the denominator for their probability answer, and in the numerator, it's going to be the number of cards that have the look that I'm looking for. So I could mindlessly start to write down answers for each of the 4 parts A, B, C, and D by just simply making a fraction that has a 52 in the denominator, because I'm selecting 1 card from a deck of cards that has 52 cards, and it's not a conditional probability. I wasn't given any extra information about the card that was selected, so the denominator is 52. And then the numerator is going to be the number of cards that have the look that I want. And for part 3A, the non-red cards in a deck of cards are the spades and the clubs. there's 13 spades and 13 clubs. That's a total of 26 cards that aren't red, and that fraction reduces to 1 over 2. So for each part of number 3, the numerator is going to be the number of cards that fit the criteria that's presented in the question, and that involves knowing what a deck of cards looks like and all the cards and how they're classified. Part B, there's only one card in the deck that's the 7 of spades. That is specifically the 7 of spades. And so the numerator for part B is just going to be 1 because there's only one card in the deck, and it is the 7 of spades. C is the tricky part. If in C you write 17 for an answer, you're double counting the 6 of spades. So for the 6, there's a 6 of clubs, a 6 of diamonds, a 6 of hearts, and a 6 of spades. So there's 13, there's 4 sixes that would be part of the cards that fit for my numerator. And then for the spades, there's an ace of spades, a 2 of spades, a 3 of spades, a 4 of spades, a 5 of spades. I can't count the 6 of spades twice, so because I counted it as a 6, I'm not going to count it again as a spade. And then if I do the rest of my spades, there's a 7 of spades, an 8 of spades, a 9 of spades, a 10, a jack, a queen, a jack, a queen, and a king. There's usually 13 spades that I would add for the number of spades, but because I'm not counting the 6 twice, I'm going to count the 4 sixes and the 12 spades that aren't sixes. My numerator is going to be 16 as opposed to 17. If you have 17 in your numerator, you've double counted the 6 of spades. And even though I could reduce that fraction without my calculator, I just used my calculator to reduce it. So I divided 16 divided by 52, got the decimal, then I hit math, enter, enter, and my calculator gave me the fraction reduction that I don't know if you could even see, but it's 4 over 13. And then part D is looking for a red ace. That would be the ace of diamonds is a red ace, and the ace of hearts is a red ace. So there's 2 red aces in the deck of cards. That's going to be the 2 that I put in the numerator. The 52 is the 52 cards that are possible to select when you're picking one card from a deck of cards. And if I reduce that fraction, I'll get 1 in 26. So anytime a fraction is reducible, I should reduce it. If you can't reduce a fraction in your head, you can use your calculator, do the division, and math enter, enter to figure out if the fraction is reducible. For number 4, there's a bag that has marbles in it. There's 6 black, 2 red, and 3 white. So immediately, just like I did with the dog problem, I added up those numbers. So this bag has 11 marbles. I'm drawing a single marble from the bag. The denominator for each of the probability questions that's asked in number 4 is going to be 11 because there's 11 marbles in the bag and I'm picking one of them. And it's not a conditional probability where the denominator is going to be smaller because I don't see the words if or given that in the probability questions. So this is just a straight fraction with 11 in the denominator, and in the numerator it's the number of marbles that have the look that I'm looking for. So it's similar to the card problem, but probably easier because I'm told specifically what marbles are in the bag. And so for part A, the probability that the marble that I draw is black if I'm picking one. The numerator is 6 because there's 6 black marbles. The denominator is 11. If I was picking 2 marbles, it wouldn't be so easy. For part B, the probability that I get a red or a white one, I have to count the number of marbles in the bag that are either red or white. There's 2 red and 3 white. If I add the 2 and the 3, I get 5 marbles that fit the look that I'm looking for. Both of those fractions aren't reducible 11's a prime number, so the fractions just aren't going to reduce when either the numerator or the denominator is prime. Oh, problem 4. The odds against selecting a black marble is the probability that the marble is not black divided by the probability that the marble is black. The probability that the marble is not black, there are 5 marbles in the bag that aren't black, the 2 red and the 3 white. So the probability that the marble is not black is getting one of the 5 non-black marbles over of the 11 marbles. The probability of the marble being is black is 6 in 11. And then we write this as a division problem. I go 5 over 11 divided by 6 over 11. We invert and multiply, make this 5 over 11 times 11 over 6. And then we cancel and reduce, and then write it with a colon. So the odds against selecting a black marble are 5 to 6. The odds in favor of selecting a red marble is the probability that you select a red marble, or the marble is red, divided by the probability that a red marble is not selected. So the difference between 5 and 6 were the words against and favor. Against, the not happening goes in the numerator. In favor, the not happening goes in the denominator. So I need to do each one of these probabilities. The probability that a red marble is selected is 2 in 11 because there's 2 red marbles of the 11 marbles. And in the denominator, the probability of a red marble not selected, that's picking the 6 blacks or the 3 whites, and that's going to be 9 in 11. So this is going to be rewritten as 2 over 11 divided by 9 over 11. Invert and multiply. This is 2 over 11 times 11 over 9. Cancel my 11s, and I get 2 over 9, which I'm going to write is the odds in favor of selecting a red marble are 2 to 9. So I'm going through this review at a reasonably fast pace, with the idea that you can always pause and rewind as needed. And then if I do something that's just completely horrible, then you should visit me or ask me in class exactly how to do the problem, because I'm not going into a lot of depth explaining these problems. I'm just kind of doing the problems and skipping a lot of the theory. So if you need a little more explanation, then visit me and I can try to make my answer better, because these answers just might not be sufficient for you, and it's completely okay before the test not to understand something completely, but you should not go into the test unless you can do all of these problems quickly. And the review is in kind of a nice order. The problems are written in essentially the same order as they would have appeared, one section at a time. The first problems were from section 12.1. The second problem was probably from section 12.2. On the test, that's not going to be the case. So you need to be ready to answer the questions if they're not written in the order that they were presented in the chapter. 7 asks me an odds question, picking a single card from a deck of cards. Odds require me to compute probabilities, and probabilities require me to make fractions. The odds in favor of selecting a heart is going to be the probability of selecting a heart divided by the probability of not selecting a heart. So in favor, the not goes in the denominator. So I'm doing 2 probabilities with picking 1 card, and picking cards have 52s in their denominator. So I'm going to do two probabilities. The probability of selecting a heart is going to be something over 52 because I'm picking one card, and there's 13 hearts in a deck of cards, so the probability of selecting a heart is going to be 13 over 52. The probability of not selecting a heart, that's getting any spade, club, or diamond. And there's 13 spades, 13 clubs, and 13 diamonds for a total of 39 cards. If you can write the answer for this without doing this extra work, that's good. So I'm going to just do it the long way. This is 13 and 52. I could rewrite that fraction as a division problem. I can invert this and multiply it. So this is 13 over 52 times 52 over 13. 39, should I say. The 52s cancel, and this is the first multiplication problem where we've been able to cancel more than just one canceling. This 13 and 39 cancel because 13 divided by 13 is 1, 39 divided by 13 is 3. I'd write the answer to this question 1:3. If you would have written 13 to 39, that's not reduced. I might take a point off, so it would be safe to reduce as much as you can because I think our author consistently reduced for any probability or odds question that we were asked. So 8 asks me to compute probabilities from a table, and the table problems, we had kind of two kinds of table problems in the chapter, and some of the table questions that asked us to do probabilities were conditional probabilities, and the denominator would be something, in my answer, would be something different than the total number of people that were surveyed. That would be the case if one of these questions after had the word if something or given something. As I read through the 4 questions in part 8 or number 8, I don't see anything that would restrict the denominator from being anything other than the 1,000 people that were surveyed, because there isn't the word given that or if something written after any of the questions. So for each of the parts of number 8, A, B, C, and D, I'm going to form a fraction, and for each, the denominator is going to be 1,000 because there were 1,000 people that were surveyed. And none of the questions is written in such a way that I have to look at a smaller denominator. So to get the numerators, I just look at the question and try to interpret what number or what sum of numbers from the chart that I need to get. The probability that a person that's selected as a woman, there's 400 women in favor of medical marijuana, 200 opposed, for a total of 600 women. 600 is going to be the number that I'm going to put in the numerator for my answer to part A. And when I reduce this fraction, I can reduce it without my calculator, but on my calculator I go 600 divided by 1,000, and then math, enter, enter. 3/5 would be the answer I'd be hoping to see on the test if this was a test question. For part B, I want to find the number of people that were in favor of medical marijuana. There were 300 men and 400 women for a total of 700 people that were in favor of medical marijuana. So the numerator to the answer for part B is going to be 700. I can reduce this fraction without my calculator because I can just delete 2 zeros from the numerator and 2 zeros from the denominator and get 7 and 10. So the answer for part B is 7 and 10. C is looking for a man that opposes medical marijuana, and there are 100 men opposed of medical marijuana. So the numerator is going to be 100. I can reduce that fraction by just crossing out 2 zeros, and I'll get 1 in 10 for a simplified answer to part C. And then part D is a woman that favors medical marijuana. That's these 400 women. They're women, they favor medical marijuana, so that's going to be 400 in 1,000. I could reduce this without my calculator. Without my calculator, I just cancel the 2 zeros and get 4 and 10, and then I reduce it again to 2/5. So the best answer for 8D would be 2 and 5. So of the chart questions, this was much more, it's going to be much friendlier than the next chart probability question. The next chart is a little bit bigger, and it has some conditional probabilities, so all the denominators won't be the same number. Nine wants me to make a sample space. You don't absolutely have to make a sample space, but for a couple having 4 children, the sample space is kind of large, and getting one constructed might help. So I'm going to make a tree. The first kid could be a boy or a girl. The second kid, regardless of what the first kid is, can be a boy or a girl. The third, regardless of what the first 2 are, can be a boy or a girl. And the fourth, regardless of what the first 2 are, can be a boy or a girl. And so I'm just going to, without explanation, kind of follow the tree to each of the B's and G's in the bottom row. And there's going to be 16 B's and G's in the bottom row. So there's going to be 16 elements in my sample space. This B right here is just getting a boy for the first kid, a boy for the second, a boy for the third, and a boy for the fourth. This G is a boy first, boy second, boy third, and girl. Done with that, I go to this B, that's a boy, boy, girl, boy. Go to this G, it's a boy, boy, girl, girl. Now this way I'm going to go boy, girl, boy, boy. And then boy, girl, boy, girl. And then boy, girl, boy. I did that already. So boy, girl, girl, boy. And then boy, girl, girl, girl. The nice thing about the second branch is it's going to give me almost the same sample space as the first B did, except the first thing is going to be a G. So I'm just going to cheat a little bit, and next to each element that I've written, I'm going to write essentially the same thing, but I'm going to change the first child to a girl. And I could just go down the tree to get that sample space. This is quicker though. So that's the sample space. There's 16 elements in the sample space, and you definitely can just get the sample space by going down the tree. Each of the probability questions doesn't contain the word given that or if, so none of these are conditional probabilities. The fact that none of the probability questions are conditional probabilities lets me start each problem by making the denominator of my answer to be 16. The numerator is going to be the number of items in the sample space that have the look that I'm looking for. For part A, there's only one of the 16 that have all boys, so the numerator for part A is going to be 1 in 16. Part B is going to be any of the sample space that has at least one girl, which would mean 1, 2, 3, or 4 girls. And all of those that I just circled with something that looks something like the state of Michigan backwards, all of those 15, if you look at what they have in common, they all have at least one girl. Some of them have one girl, some have two girls, some has three girls, some have four girls, but they all have at least one girl, because at least one girl in this case would be 1, 2, 3, or 4 girls, so the numerator is going to be 15. Neither part A nor B have fractions that reduced, so I'm not going to have to worry about reducing them. My probabilities, the youngest child is last. For the youngest to be a girl, that one has the youngest as a girl, that's 1. There's another, that's 2, 3, 4, 5, 6, 7, 8. There's 8 items in my sample space that have the G written last, that's having the youngest as a girl. So this is going to be a fraction that's 8 over 16, and that fraction reduces to 1/2. So just a few more questions, but I think this is where the questions start to kick up in difficulty. Maybe we're not quite there, but I think this is where things start to get a little bit harder. But I was wrong. This is actually friendlier. It's problem 11 where I think we get into the harder sections. So 2 coins are tossed. A sequence of heads and tails is recorded. I'm going to make my sample space for this. There's only going to be 4 items in my sample space, so it'll make quickly. If I'm asked probability questions with coins or babies, usually we make a sample space. The sample space for this would be getting a head first and a head second, a head first and a tail second, a tail first and a head second, a tail first and a tail second. Each one of my probability questions is going to have a 4 for the denominator, because there aren't the words given that or if written with either of the parts of 10A or B, so the denominator is going to be 4. The numerator is going to be the number of items in the sample space that have the look that I want. For part A, these are the 2 items that have exactly 1 head, so the probability of getting exactly 1 head is 2 and 4, and we'll reduce that to 1 and 2. For part B, to get at least 1 head, that's getting 1 or 2 heads in this case. 3 of the 4 items in the sample space have an H or 2 H's, and the answer to part 10 is going to be 3, or part B of 10 is 3 and 4. 11 is a problem where we're going to multiply to compute the probabilities, and it's one where I know I did the video. When I did the video, I said if you would have reduced your denominator by 1 each time, I'd live with that. But this is a probability question that fits almost identical to something that I did in a video before, something almost identical to a homework problem. And it's a drug given to 3 people. I want to find the probability that the people have a certain reaction. And for each one of these parts, A and B, I'm going to make 3 fractions. I'm going to multiply the 3 fractions. Each fraction is going to fit for one person and what they need to, how they need to react to the drug. And my denominator for each is going to be 100 because this drug was given to 100 people. If your fractions denominators go down, I'd live with it, but it's not what the author wants. So the probability that they all have a favorable reaction would mean the probability that A is favorable times the probability that B is favorable times the probability that C is favorable. And for this particular drug, 80 of the 100 people reacted favorably. So the probability that A is favorable is 80 in 100. And I'll write down another answer that I wouldn't want, but I wouldn't take points off for. The probability that B is favorable is still going to be 80 in 100. And the probability that C is favorable is also 80 in 100. The reason the denominators and the numerators don't change is because I'm using the probability from the 100 people that were tested to project onto the population, and I'm not just selecting from the 100 people that were given the test. But if you did this, you said, well, if I started off with 100 people, I picked one of, there are 80 of the people of the 100 that tested favorably. I picked one, and so there's only 79 people of the 99 left to pick that tested favorably. And then for the third person, I've picked 2 of the 80, so I have 78 left of the 98 people that I have left. If you did that for your work and gave me that as a fraction, I'd live with it, but it's not what the author wants. So I'll cross that out because it's not what the author wants. And I'll do the work that the author wants me to do. I'm going to go parentheses 80 divided by 100, parentheses, times, parentheses, 80 divided by 100, times, parentheses, 80 divided by 100. Enter, get an ugly decimal, math, enter, enter. And my calculator tells me that the answer to part A should be 64 and 125. So the probability is just over 50% that all 3 of the test subjects react favorably. So it's 51.2% to be exact. So for part B, I'm going to make up 3 fractions again. And the 3 fractions are going to relate to each person and what they need to do. A needs to react favorably and for A to react favorably, there's 80 of the 100 people that reacted favorably. B needs to have no reaction, and I did some work. There were 80 that did favorable, 15 that had unfavorable. That's a total of 95. So there were 5 that had no reaction. And our author would do 5 over 100 for B having no reaction, and C needs to have no reaction, and 5 over 100 for C having no reaction. If you made this 5 over 99 and that 4 over 98, I'd live with it, but it's not what the author wants. Now I'm going to multiply these fractions in parentheses, so 80 divided by 100 times parentheses 5 divided by 100 times parentheses 5 divided by 100 equals, so there's like a 2% chance. In math, enter, enter, I get 1 in 500, which is 2%, which is, no, 0.2% chance. The author would want us to write the answer 1 in 500 for this. If you wrote 0.002, which is 0.2%, that's okay as well. So if there's a drug problem on the test, which there likely is, this is the strategy that I want. Each fraction is going to have the same denominator. We're not going to decrease the denominator as we do the second and third fractions. 12, however, the denominators are going to decrease each time. So 11, because the people that I'm picking weren't from the 100 people that were given the test, I didn't decrease my denominator. In 12, I'm picking 2 cards and I'm replacing the cards, and I'm going to do my probabilities similar to number 11. I'm going to find the probability of each event separately and then multiply the probabilities together, just like I did in question 11, where I found 3 different probabilities and multiplied them together. I'm going to do the same thing for 12. I'm going to find 2 different probabilities and multiply them together. And because it says with replacement, each probability is going to have the same denominator. So for the first card, I'm going to pick one of 52 cards. So my fraction that I use for my probability is going to have 52 in the denominator because there's 52 cards I can pick from. And then because the words with replacement are written, the second fraction is also going to have a denominator of 52, because once I take my card out, I'm going to look at it and put it back in the deck, shuffle the deck, and then pick another card, and that card can be picked again. So the probability computations for number 12, each denominator is going to be 52 because of the word with replacement. If it said without replacement, then the second denominator would be 51. So the probability that both are black, for the first fraction, there's 52 cards in the deck, And the black cards in a deck of cards are the spades and the clubs. And there's 13 spades and 13 clubs. So the probability of getting a black card for my first card is 26 and 52. If it was without replacement, getting a black card for my second card would be 25 and 51. But because the card I take out, I put it back in, the second probability is going to be the same as the first probability. It's going to be a 26 and 52 chance again. I can definitely do this computation without my calculator. But with my calculator, it gives me the right answer anyways. So the probability that they both are black are 1 in 4. So for each part of number 12, I'm making two fractions because I'm drawing two cards. The first fraction is for the first card. The second fraction is for the second card. In part B, I want to get a spade first. There's 13 spades of the 52 cards. And then a heart second, and there's 13 hearts of the 52 cards. So the first fraction is the probability of getting a spade. There's 52 cards in the deck, so that's the denominator. The numerator is the 13 spades. The second fraction is the 13 hearts divided by the 52 cards that are left after I put a card back. And this is going to reduce to 1 in 16. I'll go ahead and do it on my calculator. So I'm going to go 13 divided by 52 times 13 divided by 52, enter, math, enter, enter, and I get 1 in 16. Part C is a 7, then a 4. So I'm going to form two fractions. The first fraction is going to be the probability of picking a 7. The second fraction is the probability of picking a 4. If the word was without replacement, the second denominator would be 51, but the word with replacement gives me 52 cards to choose from each time. First problem, the first fraction is getting a 7. There's 4 sevens in a deck of cards, 7 of hearts, spades, clubs, and diamonds. The second numerator is the number of 4s in the deck of cards, and there's 4 4s. And when I multiply these together and reduce it, I'm going to get 1 over 169. If I do this, I'd go 4 divided by 52 times 4 divided by 52, math, enter, enter, and it gives me the 1 in 169. So every probability answer that I give, I'm going to make a reduced fraction. Unless the fraction doesn't reduce, then I could either give the non-reduced fraction or a decimal approximation with 3 decimals worth of accuracy. 13 wants me to roll 2 dice, and I see the words if. And the word if is a conditional probability, and my denominator for each of the parts isn't going to be, in this case, 36, which is the number of things that can happen when you roll 2 dice. I'm going to quickly write down my sample space. I kind of have it memorized for dice. So my first dice could be a 1, and then my second dice can be any of the numbers 1 through 6. There are definitely explanations of how to get this sample space given in a video somewheres. So I'm just doing first dice, second dice. The first dice can be a 2, and the second dice can be any of the numbers 1 through 6. And then the first dice can be a 3, and the second dice can be any of the numbers 1 through 6. There's going to be 36 elements in the sample space, and if the questions didn't have the word if, my answer for the probability question would have a 36 in the denominator. But once in a probability question, I see the words either if or given that, I know that the denominator is going to be less than the denominator if that word didn't occur. So in general, when I'm rolling 2 dice and I'm asking probability questions, my denominator would be 36 because there are 36 pairs of numbers that could come up writing a first dice and a second dice. For part 13a, I need to look at the portion of the sample space that has the criteria that I want. In 10A, I'm told that the first dice is a 4. So I know that one of these things had happened. Either I got a 4 then a 1, a 4 then a 2, a 4 then a 3, a 4 then a 4, a 4 then a 5, or a 4 then a 6. So the if part, if the first dice is a 4, so I know that one of those 6 things happened. What's the probability that the sum of the dice is a 10? Well, if a 4 and a 1 are rolled, the sum of the dice is a 5. If a 4 and a 2 are rolled, the sum of the dice are 6 if I just add up the numbers. And for each one of these pairs, I can find the sum of the dice. And of these 6 possible things that happened, only one of them, the last one, has the sum of the dice being a 10. The probability answer for 13A is going to be 1 in 6, because of the 6 things that might have happened, only one of them has a sum of 10. B says, what's the probability the sum is even if the second dice is a 2? I need to take the portion of the sample space that I'm worried about. In this case, that's the portion of the sample space that has the second dice as a 2. So the answer that I get to part B, the denominator for that probability isn't going to be 36, it's going to be 6, because the if part tells me I'm only looking at this portion of the sample space. And there's 6 things in the sample space that have the second dice 2. Now let me sum these up. 1 and 2 is 3, 2 and 2 is 4, 3 and 2 is 5, 4 and 2 is 6, 5 and 2 is 7, 6 and 2 is 8. The numerator for this answer is the number of items in this portion of the sample space that fits the criteria. And the criteria is the sum of the dice is even. There's the 4, the 6, and the 8 are even numbers. So 3 of the 6 are even, and the answer to part B is going to be 1 and 2. 14, the table is pretty involved, and you might have to spend some time just kind of trying to figure out exactly what the table has given me before you answer the probability questions. So 100 people were surveyed. That's the 100 in the bottom right-hand corner. And some of the people that were surveyed had auto accidents. Some of them didn't have auto accidents. Some of the people got tickets. Some of the people didn't get tickets. And on top of it, we broke the drivers up to over 25 or 25 and younger, because somehow 25 is the magic age for car insurance. And once you get to be older than 25, sometimes your car insurance goes down. So as I look through the questions, they're all asking me probabilities. Because 100 people were surveyed, I'd like my denominators to be 100, and my denominator will be 100 for each of the probability question answers, unless I see the word if or given in the question. And very specifically, part B and C, the given that I see in those questions will make it so my denominator of that probability isn't 100. Similarly, when I did the last problem, 13, the ifs in the probability question made it so my denominators weren't 36. So when probability questions are posed, if you see an if or a given, then the denominator is going to be less than the total size of the sample space. In 14, 100 people were surveyed, and that 100 is going to be the denominator of any probability question that doesn't have an if or a given that in the question. For part A, there's not a given, so the denominator is going to be all 100 people, and I need to count in my table the number of people that had an accident but didn't get a ticket, and that's all of these people. There were 20 people over 25 that got an accident that didn't get a ticket, so it probably wasn't their fault, and 4 that were 25 or younger that hadn't got an accident that didn't get a ticket. The numerator for part A is going to be 24. I can reduce this without a calculator, but I'll use my calculator to be safe. So I'll go 24 divided by 100, math, enter, enter, and I get 6 and 25. So the answer to part A that I'd be looking for is 6 and 25. For both parts B and C, my denominator isn't going to be 100, and I'm only looking at a very focused portion of the sample space. And B is tricky, as tricky as C. They're both tricky because the table's so big. So what's the probability that the person was over 25 given the person got a ticket? So if I look at this, these are all this is the portion of the graph or the chart where people got tickets. And very specifically, there were 40 people that had no accident and got a ticket, so maybe just speeding or running a stop sign or something, and 36 that had an accident and got a ticket. The denominator for part B is the 76 people of the 100 that were surveyed that got tickets. So there were these 40 and those 36 got tickets. So I'm only looking at this block of the sample space. I'm not looking at the far left column or the far right hand columns because I'm only looking at the people that received tickets. There are 76 people that received tickets. Of these 76 people that received tickets, the numerator is going to be the number of these people that were over 25, and the numerator is going to be this 15, the people over 25 that didn't get an accident and received a ticket, and the 21 that were over 25 that got an accident and received a ticket. The numerator of the probability part for part B is going to be the 15 plus 21, which is 36, and I wrote this should be 76 in the denominator if I added those properly. In the numerator, 15 and 21 is going to be 36. So the answer to part B in a non-reduced fraction is 36 over 76. And when I reduce that, I get 9 and 19. So the probability answer for part B, the probability that the person was over 25 given they got a ticket, is 9 and 19. For part C, the question is, what's the probability they got a ticket given they were over 25? The portion of the sample space that I'm looking at is just the line that corresponds to over 25. The denominator for the answer for question C is going to be the total number of people that were over 25, and that's this 56. The numerator is going to be the number of people in that row that got a ticket, and it's the same 15 here that were over 25 without an accident that got a ticket, and the 21 that were over 25 that got in an accident and got a ticket. That's going to be the same 36. So the fraction is going to be 36 over 56, because 36 of the 56 people that were over 25 that were surveyed got a ticket. And that reduces to 9 and 14. That problem feels tough, so hopefully it wasn't overwhelming. If you need more complicated problems, then I can try to do some in class if you need to see some more bigger tables, because I'm not sure the author made tables that were this complicated. But this hopefully isn't beyond you. Okay, so that's the review. Once you get done with the review, and if you feel good about it, then you should be ready to take the test over the first 6 sections of Chapter 12, which is going to be 60 points. I don't know, maybe 20 questions at 3 points each. Or, where I would count 14 as 3 questions because it has 3 parts. And then once you get done with that, you can start working on the last half of Chapter 12, which are sections 12.7, 12.8, 12.9, and 12.10. And there's going to be a take-home test worth 40 points for that particular part of the chapter. And I think it's, again, 20 questions, except they're going to be 2 points each. So the questions aren't going to be worth a lot of points on the take-home test, which means you can't get much partial credit. if a question is worth 2 points, if you make any mistake, it's going to be at least a -1, which it's kind of like a 50% on that question. So you have to be real careful on the take-home test.